have the card.
Okay, thank you. So Gordon Moore was one of the co-founders of Intel, and he noticed that the density of transistors on an integrated circuit doubled about every 18 months. Became known as Moore's Law. Well, we've kind of run out of Moore's Law, but that doesn't mean innovation isn't still happening. I mean, we have all these new innovations coming on with the quantum computing and so forth. Well, and there's also been some great innovations in imaging technology as well. And it's kind of, the more I've been working on this as an engineer, I've come up with some ideas on really we kind of need to look at our imaging a little bit differently. So CMOS is the new CCD. The equipment, the way we shoot, really there's different ways of doing it that it will enable us to get even better images and faster. There's been a lot of advances in editing, and so we'll talk about that and some conclusions. So I'll start with a table. I probably shouldn't do that, but don't want to put everybody to sleep right off, but if you could just bear with me on this one. We'll notice that we have two CMOS chips here, two cameras, the 1600 and the 183, and then an older CCD camera. So that was kind of the standby. The KAF 3800 or 8300 was the kind of what used to be the go-to for a lot of people that did imaging. Well, we see that the size is a little bit smaller, but we have a lot more resolution. So we have a lot more pixels to work with. Now, somebody will say, well, but we have smaller electron well size, which means how many electrons can we hold in each pixel. But if we look at the square microns, compare pixels and to pixels, we'll find that we actually have more well size. We have quantum efficiency is better. That's quantum efficiency is how many photons actually get converted into electrons. So 60%. The newest generation is in the 80%. The older CCDs were in the 50s, or even the older ones were even less than that. Dynamic range, that's how much from the darkest to the brightest can we capture. That's the dynamic range. It can be measured in stops. And so on the newer cameras, we're looking at a little bit better dynamic range, in addition to all the other advantages. Now when you're doing astrophotography, the whole thing, in a nutshell, remember this if you don't remember anything else, the biggest thing in astrophotography is signal to noise ratio. Well, we can't turn up the signal, we can't make the stars and the nebula any brighter. Well, we can use a faster telescope. But really, the only thing that the biggest thing that we have control over is the noise. So if we can mitigate noise anywhere we can, that's all happiness. So we can see that one of the things, they call it read noise, it's really the analog to digital conversion noise because there's rounding errors and other errors creep in there. 1.2 electrons, 1.6 electrons. CCD was 16 electrons. So we have an order of magnitude better noise in the read noise. And of course, also much faster. So when you're doing planetary capture, 1.9 frames per second is not really going to do a lot for you. The newer cameras have much faster frame rates. So smaller pixels means that we have magnified resolution. So we can have the exact same telescope, the exact same magnification on that telescope, but if we put a sensor on it and that sensor has smaller pixels, we're now packing more pixels into whatever image that we had with the CCD sensor. So we get a magnified resolution. Of course, the higher quantum efficiency means that we have shorter exposure times. I'm kind of an impatient astrophotographer, and so shorter exposure times is all good for me. Much faster read time, so we can get up to hundreds of frames per second. They put USB 3 ports on these, and we can get literally hundreds of frames per second with what's called a region of interest, where we're looking at a smaller portion of the CCD sensor. Much less power. The CMOS is much less power than the CCDs. In fact, the entire sensor can be run off of the USB port. Used to be you had to have a USB or whatever communication port, and you had to plug it into 12 volts or whatever. Still have to run 12 volts if you're running a fan, but the sensor itself will run just perfectly from the USB port. It's cheaper per square millimeter. And then there were problems with CCD technology, bloom and residual bulk image, in other words, burn-in. So that's not, we don't have that on CMOS anymore. Now, one of the biggest innovations that have come around with the new CMOS technology is called backside illumination. The way that it's easy to make chips is to put the photodiodes on the first layer next to the silicone, the silicone chips. So you lay down those photodiodes and then put all the logic electronics on top of it. It's actually easier to do that way. And that's the way it used to be done. So you literally have all of the wiring that's wiring all these photosites together. The light has to pass through that wiring to get down to the photodiodes down here. Let me turn this on. So here's our photodiodes, here's our wiring. Have to pass through that. The backside illumination, the BSI chips, now we've put the photodiodes at the top where you don't have to pass any through any electronics to get to those photodiodes. That is why we have a higher quantum efficiency. Also, because of that, they're able to make a little bit bigger electron wells. An electron well is really a capacitor, if you're familiar with electronics. It's just a plate where electrons are able to be gathered. And so the bigger the plate, the more farads, or probably femtofarads, and we're able to capture more electrons in a given square micron. So the backside illumination gives we have a larger sensor area per pixel, larger aggregate well depth. So on this ASI 1600, our new CCD, it has 3.8 micron pixels versus the 8300, the CCD version. Well, that gives us 76,000 electrons in the same square micron area as a single pixel of the CCD, which that CCD had, I think, 25,000 electrons. So actually we have more electrons that we're dealing with here. And these wells are filling up faster, which means shorter exposures. So we have equal or better usable bit and electron well depth. Less read noise means that we have more of our well we're able to, or more of the conversion we're able to actually use as part of our signal. Less noise doesn't give us more signal, but it allows us to filter out more of the noise and then have the signal left over to deal with. Sensor area covers the whole pixel. So you don't, with the CCDs, you had one little area of that 9 microns. One little area of it was the actual sensor. The rest of it was all the electronics and everything else around it. Whereas with the backside illumination, we have bigger areas to gather stuff. So we have more efficiency. Now, I need to explain, let me see something here. Nope, wasn't that one. I don't know why that keeps popping up. The ADU is the analog to digital unit. So, everything's ones and zeros, it's all bits. And every bit means that we're either doubling or halving some number. So 5 is 1, 0, 1. So we have 1, 2, 4. So 1 plus 4 gives us 5. That's how digital works. Well, each one of those ADUs, each one of those analog digital units is telling us a certain number of electrons. So if we have, say, 4,000 electrons and our analog digital conversion only goes from 0 to 4,000, then we have 1 electron per ADU. If we have more electrons, then that means we have more electrons per ADU. So the fact that the CCDs had 6 electrons per ADU means that we're imaging 6 times longer than we really have to. Now there are some noise advantages to that. It's called shot noise or Poisson noise, but all of the other advantages wipe out that. So I just want to talk just for a second. I need to tell you about equivalencies. You'll hear a lot of terms bantered around. They're all talking about the same thing. So dynamic range, number of bits. So if you have a sensor that's able to capture 16 bits of information, that's 0 to 65,000. So it's able to capture that number of bits. Well, guess what? There aren't any yet, but they're coming soon, I hope. Stops of exposure. So if you look at a professional camera, they'll talk about how many stops of latitude does a given camera have. Exact same thing as dynamic range of bits. And then you'll also hear, they'll talk about signal to noise ratio. Well, every 6 dB is a doubling or halving of the noise of signal to noise ratio. So they're all exactly equivalent. 1 bit equals 6 dB equals 1 stop. So you'll hear, depending on whether you're talking to photographers, you're talking to chip designers, or you're talking to somebody about astronomy cameras, they're all talking about exactly the same thing. So back to our little chart here. When we look at, no, I'm sorry, that was, okay, so each digit represents the number of electrons. So if we have a 12-bit, for instance, we can count up to 4096. If we have 3 bits, we can count up to 8 digitally with the binary. So if we have 12 bits, we can count up to 4095 and 0. So it's 4096. So if we're gathering our electrons, or photons, are being converted to electrons, if we're gathering more than 4096, we're wasting time. I don't like to waste time. If we're gathering less than, that would be undersampling, then we're throwing away information that we should be processing. So we decrease our precision. So unity gain, there's this little magic thing called unity gain. CCDs don't have the type of gain that CMOS cameras have. CMOS cameras, you can dial in pretty much any gain that you want. And so we can set a CMOS sensor to unity gain ADU. So we figure out what that magic number is, and then we're not wasting time, but we're gathering all of the data that we need to get all of the precision that this chip is able to give us. That's where we want to be, right? So in deep sky object, DSO, we need a large sensor. A lot of these deep sky objects are big, and so we need a larger sensor to grab them. We need a high quantum efficiency. A high dynamic range is good. A lot of megapixels never hurts. When cameras first came out and they kept talking about, oh, it's so many megapixels, that was kind of like, well, they're kind of doing a shell game here. But when it comes to astronomy cameras, megapixels is a good thing, provided that all of the other goodness that we have in CMOS is there. Low read noise in the dark current. We'll talk about dark current in a minute. And thermal electronic cooling, TEC. And I'll explain why we need TEC in a minute. So the ASI 1600, the red part of this camera right here, or the red part of this whole assembly here, this back here, that's the camera. It probably doesn't look like the one that you use at home, right? That's an astronomy camera, and they all kind of look funky in one way or another. Some of them have the filter wheels built into the camera, but this one has outboard. So the actual imaging chip is inside this camera here, and you can physically see it. I'll have to clean this later, but I'll go ahead and show it to you right now. So there's the actual chip. You can see that little rectangle that's down inside there. That's the actual chip, and it's called a micro 4/3. So it's 4/3 of an inch, which only people that design cameras know why they use thirds. I don't know, but so that's the sensor part of it here. And then this fin part back here, that's the cooling part of it. So it's a two-part deal. So you can see that's a pretty good sized chip. It can be monochrome or OSE, one-shot color. Every camera, your cell phone camera, your point and shoot, your professional camera, those are all one-shot color. You take one picture and you have all the colors are available. When we do astrophotography, we need more precision with our colors, and we need to gather more light per color. And so we'll use a monochrome sensor, which you can only see black and white, but we will put red, green, and blue filters separately. They're on this wheel here, and we'll bring up the red filter, we'll bring up the green filter and the blue filter, and take as many images using each one of those colors. It's kind of a long drawn out process. So that's a one-shot color versus monochrome. So it's 18 by 13, 3.8 micron pixels. It's a 16.6 megapixel camera. Quantum efficiency is 60%. Now, dark current is why you want to buy a cooled camera. So dark current of this camera, which I always shoot at minus 10 degrees Celsius, is 0.0083 electrons per second per pixel. Well, I don't care about per pixel. All I care about is electrons per second. So if you multiply that out, that's about 1 electron in 4 minutes. In other words, it's really not a lot of noise. The older CCDs, they had much, much higher ratings. And if you don't cool, you get a much greater amount of noise. So you always want to, people, you see, you can buy cameras that have been modified. You can buy a modified DSLR. Well, what they've done is they've taken off that, there's a filter that helps to balance out the red. So take that red filter off for $350. You've just thrown away $350, in my opinion. Because this is going, remember, it's not about signal so much as it is noise. And if you can cut down the noise, you're way ahead of the game versus signal. So the unity gain of the 1600 is 139. Now another little thing, this is, I'm not charging you extra for this, but when the gain is being done, it's multiplying, and everything is all binary. So if we multiply by binary numbers, then we get better precision. Because if we have to multiply by some number that's between binary numbers, then that has to be interpolated. That adds noise, okay? So we always want to multiply by some factor of a binary number. The way that ZWO talks about gain is in centibels. You've all heard of decibels? Well, in other words, 10 times a decibel. So 139 is 13.9 decibels. Ooh, that's a number we know about. Decibels. And we know that 6 dB is a doubling or halving, in other words, a binary number. So we don't want to use 139, we want to use 120, 12 dB, or 180, which would be 18 dB, but now we're throwing away electrons because we are over amplifying the signal. So I shoot, everything I shoot is at 120 since I've come up with these ideas. Last year, or whenever it was, I told you this, I was shot at 300 actually. Because I shot at 300 because that is the lowest point for read noise. Well, guess what? I don't care about read noise anymore. I'm not shooting with a CCD. I don't have 16 electrons of read noise every time I read a bit out of a pixel out. What I have is 1.6, so I'm already way ahead on read noise. Much better off to concentrate on getting that unity gain ADU, which for this camera, I highly recommend 120. So full well at 120 gain is 5,000 electrons. And that's 11.5 stops of dynamic range, which is really pretty good. 1.7 electrons read noise, very, very nominal. And because we're only getting a couple of electrons, you know, if we did a 10-minute exposure, we're only getting 2.5 electrons from our current, dark current. So now my offset, which used to be when we're shooting CCDs, you had an offset of 10, 15, 20. Well, I can do an offset of 4. So I'm getting more gain and just covering up, just burying the noise in the offset. Just announced, ZWO and QHY have announced cameras based on the IMX 455. It's a full frame. It'll be monochrome or one-shot color. You know, full frame, 36 by 24 millimeters, 61 megapixels. Kind of looking forward to that. Not looking forward to being broke, but quantum efficiency is over 87%. So every photon, or 87% of all the photons, get converted into electrons. Very, very efficient. 13.8 stops. And I was excited about 11.2. So I can't wait to get that one. So that was DSO requirements. Planetary, we need fast frame rate. I don't know if you remember the Saturn and Jupiter shots. Those are like 20,000, 30,000, 40,000 frames were gathered. Well, the problem with those planets is they rotate every 10 hours. So you can't just sit there and shoot them for hours on end at a slow frame rate. You have to really crank up the frame rate, shoot them for a short time, and then there's a little program out there called WinJupos that helps to de-rotate whatever rotation you did capture. We need high quantum efficiency and dynamic range. That's just, you know, for everything. Those little tiny pixels, the smaller the pixels, the better intrinsic magnification that we get. Now, 2.7 micron, which is the camera I'm going to talk about next, is, you know, we're talking about 2,700 nanometers. That's infrared light. And when you sample stuff like that, there's this thing called the Nyquist, which means, you know, if you want to capture 1,100 nanometers, which is infrared light, that's about as far as you're ever going to get. So as far as pixel size, 2.7 microns, 2.4 maybe. But below that, now you're starting to cut out infrared. And infrared is really handy. If you haven't experimented with infrared, there's a lot that can be done with it. So we need usable noise. Because we're stacking 40,000 frames, noise is kind of factored out. But still doesn't hurt. So the ASI 183 is great for planetary. It's a 1 inch. Now this is 1 inch from the film people. You know, well on film, the film is 1 inch wide, but you have sprockets on either side, you have a soundtrack. So by the time you get done with actually making the film usable to shoot cinema, you end up with a 13.2 millimeter wide by 8.8 millimeter. Now this has 2.7 micron pixels, really small. It's 20 megapixel camera. It'll shoot 80 frames a second at 1920 by 1080, which is high def, if you didn't know that. So 80 frames a second, that's pretty good. You know, well, I'll talk more about that. Quantum efficiency, 84%, really good. You can get really, really fast shutter speeds with that. Unity gain, surprise, surprise, 12 dB again. So I set it for 120. At that rate, my full well is 4,000, so I am undersampling just a little bit, but I still have 10.8 stops of dynamic range, which is really good. 2.2 electron read noise. So that's why I'm just basically telling you everything I used to shoot that. So it's an Edge 14 power mate, 2X power mate, which is like a Barlow. Is that better? The atmospheric dispersion correction, that's needed, especially here in Houston, because the way that the planets are aligned right now, the Jupiter and Saturn are kind of pretty low on the horizon, and so atmospheric dispersion becomes a problem. ZWO makes an atmospheric dispersion corrector for about 130 bucks. Money well spent. So at that, with an edge at 2x, we're looking at about 8,000 millimeters f22. I still have 50 millisecond exposure time, which is pretty fast, with a gain setting of 270. So when it comes to shooting Planetary, I don't really care about the gain situation. I can crank up the gain as long as I get a reasonable noise. So this was shot in 2 stages, one shot color for getting the color, shot a few, I don't know, probably about 10,000 frames of that, and then shot another 20 or 30,000 frames with an infrared filter. Now you can't do this visually, but with a camera where you can shoot in the infrared range, the infrared sees right through the atmosphere. So all of that seeing problem that you've been experiencing is almost eliminated. So infrared is really good. You want to have infrared. Derotate when JUPOS, and I did a 3x drizzle on this. So this file is 3,200 pixels across. It's really big. I mean, we could print this, 20 inches and not lose any resolution. So I love those tiny, tiny little pixels, especially for Planetary. Now, interesting thing about the 183, because it has such a high quantum efficiency and all these other things, at hydrogen alpha, which is a deep space object, most of those deep space, the red ones, that's hydrogen alpha. So all of those objects out there, the quantum efficiency of the 183 at hydrogen alpha is 60%. And so back to that CCD chip, the quantum efficiency of hydrogen alpha on a monochrome version was 25%. So with a one-shot color, we are blowing away the CCD camera. And it keeps on par with the 1600. Dark current, negligible, 16 minutes per electron. Don't worry about dark current. There is no dark current. If you have a cooler on that camera, there virtually is no dark current. Unity gain, okay, I'm repeating myself, aren't I? Okay. So this was shot with the one-shot color camera, RGB, and then I have a hydrogen alpha filter I put over that same one-shot color camera and enhanced the hydrogen of this cloud. This is called the Pac-Man Nebula, and with the hydrogen alpha on a one-shot color camera. Don't try this with a CCD, it won't work. Not a color. Here's another one, hydrogen alpha. This is the crescent, thank you. Doing so well, and then that. Okay, this is 5-minute exposures. Color image was stretched and converted to mono in post-processing. What came out of the camera was red. I mean, it was really red. But we can take care of red, that's no problem. We make it whatever we want in post-processing. So 30 frames at 5 minutes each, minus 10 Celsius, 120 gain. This is what we get.